Hello all, welcome back to my YouTube channel all about VLSI. We are going to discuss, we have basically discussed about PCA protocol, and like we have seen the advantages and disadvantages of PCI and why we are shifting to PCIe. We have discussed those kind of things. And before going to start with the architecture of PCIe protocol, let us try to understand few more basics which are related before we need to know before starting PCIe protocol, right? Now, here, let us try to understand something known as North Bridge, South Bridge, and Front Side Bus, that is FSBN. What are these particular technical terms? Because in PCIe, when we are going to refer, we are going to get this kind of terminologies and all, right? Now, first of all, what we are going to cover in this particular session is we are going to discuss what do you mean by a chipset and why we are going to use a particular chipset, and what do I mean by north bridge, what do you mean by south bridge, and what is mean by front side bus and all we are going to discuss in great detail. So basically, let's say if I'm going to have a processor which is having so many peripherals like a RAM or a DDR memory and a graphics card and a storage card and a USB peripherals and all, my processor is not going to directly communicate with all these particular peripheral components. So a processor is not going to execute all these particular processes inherently, and these are basically having fundamentally different electrical protocols operating at different speeds. Whatever the peripherals which we are going to connect to my processor, every particular peripheral is going to have their own specific kind of protocols and they have own specific type of speeds. And the CPU obviously needs intermediate circuitry that is going to speak to all these particular languages and routes traffic between them. Now, so here my CPU is not going to, deal this with this all kind of peripheral protocols, and obviously it needs an intermediate circuitry. Now, uh, we are going to have something known as chipset over here. Basically, a chipset is support chips on the motherboard that handles communication pathways between the CPU, memory, and all peripheral devices. Where the CPU is a computational brain and the chipset is the nervous system. So you can see over here, we are going to have our CPU present over here, and the CPU is not directly communicating with all the particular peripherals, but it is using something known as a chipset. So this particular chipset is helping CPU to establish the communication between this particular CPU and all the particular peripherals. So from late 1980s through mid 2000s, the intermediate circuitry was implemented as a two chipsets which sold alongside with the processor. So alongside with the processor, they have sold this particular two chips. So one of the chip, you can see this particular upper one is known as north bridge and the lower one is known as south bridge. So this north bridge and the south bridge together forming the chipset that turned a particular CPU into a functional computer. So this is nothing but my chipset. Now, so basically, we are going to have two chips. One is North Bridge. Let us first of all try to understand what do I mean by North Bridge. So this North Bridge sat directly adjacent to the CPU on the motherboard, connected via the system's fastest link. That is nothing but my front side bus, which is nothing but my FSB. So you can see in this particular diagram, this is my CPU, and this CPU is connected to this particular North Bridge. Okay, whatever the chipset I have told you, right? So in this particular chipset, I'm going to have two chips which are present, and this is my north bridge and this is my south bridge. And this north bridge and the CPU are connected via a particular high bandwidth device which is known as front side bus. Okay, this is the fastest link which is present on my particular entire board. And the name of this particular north bridges came from the architecture, system architecture, typically drawn with the CPU at the top and devices cascading downwards. Okay, so that's the reason. Basically, this particular north bridge is upward to your CPU. That's the reason it is set to as north bridge. Now, so its memory controller was the core architectural reason for its existence. DRAM latency directly limits CPU performance. For example, if I'm going to have a CPU, and if the CPU wants to communicate with this particular DRAM and wants to perform memory operations, definitely there will be latency introduced due to this particular memory operations. So that's the reason what CPU is going to do. It is not going to directly deal with the DRAM. It is going to give those particular memory operations to the north bridge. So north bridge internally going to have something known as memory controller. So north CPU is going to give the instructions to the north bridge that perform memory operations to the DRAM. So internally north bridge is going to have something known as memory controller. This it is going to deal with this particular DRAM. So by reducing the latency, and if we are not going to have this kind of north bridge, and we need to implement this particular memory operations directly, and the CPU is going to get the latency. So that's the reason we are going to use here north bridge, which is going to contain a particular memory controller and helping us to basically decrease the DRAM latency. Now, so the responsibilities of this particular north bridge chip is basically, these are the responsibilities of this particular north bridge chip. So north bridge internally it is going to have something known as memory controller, where it is going to have direct interface to the DRAM like DDR, DDR2, DDR3, and every particular CPU read or write to RAM went through the north bridge. So if my CPU wants to perform any particular memory operation, it is going to happen via this particular north bridge itself. And one more responsibility is graphics interface. So AGP in late 1990s, later PCI X16 for discrete GPUs. So bandwidth too high for South Bridge. So South Bridge cannot deal with high bandwidth operations. So North Bridge is only going to have the interface to the graphics interface also. And next is front side bus interface. So what do I mean by front side bus interface? So the CPU facing port, it is going to basically receive all CPU memory and input output requests. So this particular front side bus is going to connect my north bridge to my CPU, and it is going to facilitate all the particular high speed memory operations and input output requests which are getting from my peripheral devices. And one more thing is north to south link. So I'm going to have a proprietary high speed bus connecting down to the south bridge for slower peripherals. So whatever the slower peripherals are present, that will be connected to your south bridge, and there will be a proprietary connection between your north bridge and south bridge, which is going to connect your north and south bridge. So you can see over here all the peripherals, all the slower peripherals we are connected to this particular PCA slots, and this particular PCA slots are connected to this particular south bridge. And this is nothing but my north bridge responsibilities, and just a brief description of south bridge. Now, so why everything fast connected to my north bridge? You can see over here the CPU is present over here, and CPU is not directly connected to RAM and GPU. Basically, it is connected via this particular north bridge, and we are going to have something known as FSB, which is nothing but my front side bridge. So this is nothing but my front side bridge. Now, so basically, North Bridge memory controller was a key architectural reason for its existence, because DRAM access latency and bandwidth directly limits CPU performance. So if my CPU is directly going to access the DRAM, then obviously the performance of my CPU is going to reduce because of the latency in the memory operations. So memory controller had to be close as possible to the CPU. So that particular memory controller is directly implemented in my North Bridge. So North Bridge implemented this particular controller, and therefore had a direct high speed connection to both CPU via the FSB and RAM via the memory bus. So RAM is also going to access this CPU via this particular FSB and via the memory bus with a separate port for the GPU, since graphics was only other device demanding comparable bandwidth. So this GPU is going to have its own separate bus, and RAM is also going to have its own separate bus, and North Bridge is connected to this particular CPU via the FSB. So this is how your North Bridge is helping and trying to reduce the latency. And coming to South Bridge. So basically, the South Bridge sat below the North Bridge, connected to it via a proprietary interchip link, and it is going to handle the slower, lower bandwidth peripherals that that basically did not justify a direct connection to the fast North Bridge. So whatever the lower speed peripherals are which are present, that are not directly connected to the North Bridge, but these particular lower speed peripherals are connected to my South Bridge. And over here the responsibilities of my south bridge is, it is going to act as a PCI bus controller. So the south bridge is going to act as a PCI bus controller, and it is also going to act as a USB host controller, and it is also going to act as a SATA or IDE controller, as well as it is also going to act for HDA audio, and LPC bus and SMC bus. So all the peripherals are connected to my south bridge, right? Now, so here the south bridge did not need to be fast, it needs to be comprehensive, and it is a very highly integrated chip that it is going to implement different kind of protocols. South bridge is going to implement a different kind of protocols. You can see over here so many different protocols are implemented in the south bridge. And speed was never the design goal, and feature integration and cost were reduced. So basically a single south bridge chip replaced what would otherwise have been a dozens of individual controller chips on a 1980 era's motherboard. So if I want to implement this kind of different kind of protocols, I need to have different memory controller or different kind of protocol controllers, right? So different chips I need to have, different controllers I need to have. So that was basically integrated into a single chip, which is nothing but my south bridge. So if I want to briefly recap, north bridge is basically a connection between my CPU and the high speed devices like your DRAM and your GPU and all, and directly CPU involving and accessing those and communicating with them. My north bridge is going to take care of them, and south bridge it is going to take care of all the peripherals which are connected to this particular south bridge, and there will be a connection between this particular south bridge and the north bridge, and the CPU and north bridge are connected via the FSB. So this is how we are going to have the architecture. Now, so if I want to again recap using this particular table, so north bridge is basically present at the top of the diagram adjacent to the CPU, and south bridge is basically connected at the bottom of the diagram below the north bridge, and it is linked to the CPU via the FSB, and south bridge is indirect via the north bridge only. It is going to connect to the CPU. And the design goal of this particular north bridge, why are we using this particular north bridge, is to get maximum bandwidth and have lower latency. And why are we using south bridge is to have maximum number of protocol coverages and to have lesser cost, because we are implementing everything in a single particular chip, which is nothing but my south bridge. And key devices which are connected to my north bridge are memory controller, GPU interface. And south bridge we can connect PCI, USB, audio, LPC, RTC and all. And you can have north bridge as a fastest hub, and south bridge is basically a slowest hub. So we are going to have, as I was told you previously, that we are going to have a particular bus which is known as front side bus, and was the electrical connection which was present between my CPU and the north bridge. And it is a parallel bus, it's not a serial bus. So FSB was not a serial bus, it's a parallel bus, similar to the concept which we have discussed in PCA, but it is going to run at very higher frequencies. And this particular FSB is going to carry lot of CPU request for memory input output and inter-processor communication in multi CPU systems. So this is the role of my FSB. So basically, FSB was evolved in across the time. So basically, in 1989, in Intel 486 era, basically it was 32-bit width, and the frequency was this, and it was having this particular 200 megabits per second bandwidth, and the architecture was basically processor local bus. So in 1989, Intel 486 doesn't use it any particular FSB. It basically used it local bus for communicating with other memory or GPU or kind of thing. But in Intel Pentium, we had the width of 64-bit and the frequency was this, and it used classic FSB. And going on, we have GTL plus FSB, and then quad pumped FSB and enhanced FSB in 2006 to 8. And in 2008, completely this particular FSB was eliminated. So this is what we are going to discuss, like how FSB was eliminated and what was the architecture that evolution has happened. And so this was the peak bandwidth over the time. So by 2006 to 8, the bandwidth has increased a lot. So basically, every CPU memory access, every DMA transfer, or every particular PCIe packet from a GPU, every read from a disk, all of it had to cross the FSB to reach the north bridge. So obviously, it should, from the south bridge, it should go to the north bridge, and from the north bridge, it should go to my FSB, and from the FSB it is going to the process. So this was a basic architecture, and basically it has increased the overhead over FSB, because as time increases, the bandwidth and the number of data has increased, and the reason we are going to eliminate that particular FSB, and we are going to that basically led to the evaluation of our chipset. So this is what we have seen in our particular session, where we were having a CPU and we were having a FSB, which is going to be connected to my north bridge, which was connecting to my RAM as well as GPU. And we are going to have a south bridge, which is going to connect to PCI, USB, and all other different kind of protocols. So this is what we have discussed in our particular session, where we have seen what do you mean by chipset, what do you mean by north bridge, what do you mean by south bridge, and how north bridge and CPU are connected, and how south bridge and north bridge are going to connect, and what is the role of north bridge and what is the role of south bridge. And in our next session, we are going to discuss about uh, what was the issue we were facing with this particular FSB, and how this particular north bridge is going to be converted, and what is that we are going to do with the south bridge and all. We are going to discuss in great detail in our next session. Yes, so that's about this particular session. If you like this video, please like, share, and subscribe to my YouTube channel, all about VLSI. Thank you for watching this video.